Ladies and gentlemen, my name is Jakub Wiener and I am from Technical University of Liberec. My topic, which I would like to present in this session, is materials for water harvesting collectors. Generally, this presentation is focused on water harvesting. At some places worldwide, we have problems with not enough quantity of liquid water, and some arid areas such as deserts, it's not liquid water, and water is only in the form of water vapors. But at some places, at this deserts, we have water in the form of fog. Not fog which is typical near to lakes and rivers, but fog can exist in deserts and mountains as well. If we call maybe here we can see a picture. Here I can see, but not the presenter. Some technical problems. If I press F5, maybe we can start with the presentation.
Wait a minute, maybe because it's too big.
Not so big.
This morning the presentation was different because there is the slide and also the image of the presentation.
Let's try.
Maybe we can start again.
Oh.
And maybe
No, you can continue from this point. Why? Hop. Look.
but
Now walk.
now
Now this change. Okay, go this way and we will see.
yes. So we can continue. At some places where are deserts, we can find some places with regular fog. There is possible to see daily fog. And maybe at the picture right, we can see some Namib desert with beetles. Beetles you can see if you have very sensitive eyes. And one of the beetles is up, and there you can see some collection of water droplets on this special beetle. By this beetle and some animals are inspired human activities, some collection of water from fog by industrial products, such as at this picture we can see some possible water collectors. Here we can see the most interesting solutions and materials which are used for water harvesting. At the left side we can see some knitted structure, and on the right side we can see a hard collector HARP collector will be the main topic of this presentation, but we will not speak about the full HARP collector, but about one part of this collector, only one fiber. Here we can see some materials which are used for these HARP collectors. There are approximately 30 different materials which are tested for the water collection, and maybe 10 or more than 10 from this group are monofilaments, other part are multifilaments, and yarns are tested as well. All materials are fully described by scanning electron microscopy and analysis of samples. Here we can see some generator of water droplets, fog in our case. We are using ultrasound fog generator, creating very small droplets with diameter around 4.3 microns. This size of droplets was estimated by special method, by evaporation of salt solution with set concentration. After them, we made the measurement of particles by scanning electron microscopy, and by recalculation we observed and calculated the size of particles. The fog is produced from our machine by set size of particles and concentration of water in the fog. So we have some jet creating some fog in relatively high velocity and with calculated concentration. The time of experiment was estimated or set it according to some basic experiments. We tried different times from 30 seconds till 2 minutes, and output will be that the best time will be 1 minute at our conditions, and at this time we are able to evaluate all available samples or tested samples. Here we can see maybe video presenting our experimental system. I'm not sure if it will be visible. Yes. Okay. Here we can see the jet of the fog. The white line at the picture is our sample, and on the surface of our collector we can see some creation of droplets. Here we can see the magnification of droplets on the collector. The diameter of all presented collectors is around 300 microns, and the size of droplet can be up to 1.5 millimeters. We can see that the droplet is larger in some cases than the diameter of fiber. Here we can see some group of pictures describing the creation of droplets on the collector. The time difference between each picture is 0.1 seconds. We start from the left side and there is the 0 time. And each picture it's in the time distance 0.1 second. We can see the growing of droplets on the collector. In this case it's polyester monofilament. And if the droplets are containing grow at to the limit size, they are stable on the collector. But if the droplets are enough large, they will go down around the collector and remove all the droplets from the collector at one time, at one process. This process, and we can start again. We can see that in our case, the period of this removement of the droplets, it's 1 second. Here we can see the quantity of collected water at polyester monofilaments with different fiber fineness. Or fiber diameter in our case. So if we have larger fibers as a collector of water, we can collect more water. But we can see that this dependence is not linear and not started from the zero. So we tried to make some theoretical analysis, what will be possible to collect and how to explain the behavior of our monofilament collectors. Here we can see the basic principle of collection and calculation. We know that the jet has the diameter 1 centimeter and it's in the cylindrical form. So if we add there some monofilament, we are sure how much of water can be collected by this monofilament only by the geometrical analysis. Here we have some basic calculations. Maybe this picture is more interesting because it describes the real behavior of monofilament at our conditions. We observed that the efficiency of water collection is not 100%, but only 35%. That approximately 65% of droplets are running around the monofilament and only this 35% will be collected. Other mechanism which is visible at our monofilaments is some increase of the diameter of fibers by sedimentation and growing of droplets on the fiber surface. The droplets are on the surface of fiber and the active area of fiber is increasing. The real thickness of water layer is around 125 microns. Maybe here we can see what happens at the pictures in the central part of our slide. We can see some real pictures of monofilaments with droplets. At the left side, we can see cross-sections of monofilaments with different cross-section. And at the smallest fiber, it's shown a size of droplet. If we recalculate it, we can see that at each fiber is some average thickness of layer, water layer, which increasing the active area of fiber. The thickness of this layer is around 125 microns. By this model, we can calculate the quantity of collected water and we can compare it with experimental results. We can see that at monofilaments, the theory is working properly, that the calculated values and the measured values are in a very nice connection. Now I would like to show you what is the difference between hydrophilic and hydrophobic materials. I tried, on the left side we have polyester hydrophobic monofilament without any treatment, only purified, and on the right side we can see hydrophilic polyester. It will be not easy to make super hydrophilic polyester, and maybe we can see, and we covered the polyester monofilament by nanofibers from polyamide. It was only working process. Maybe I can show you the structure. Here is a smooth surface on the left side, and on the right side we have nanofibers there. This material is super hydrophilic. And we can see that in the case of hydrophobic polyester, it's the quantity of adsorbed or collected water around 0.2 grams per minute. But in hydrophilic polyester, it's only 0.13 gram per minute. It's due to elimination of the droplets visible on the fiber surface. Maybe one of other materials which are tested, they are yarns. Yarns are very interesting fiber structures with surface hairiness. The hairiness, they are fibers which are free in the surface of the yarn, and each fiber from this hairiness, it's a collector of water. So at the yarns we are able to obtain or collect the largest droplets in comparison with monofilaments or multifilaments. Maybe at this table we are able to compare monofilaments, multifilaments, hydrophilic monofilaments, and yarn. Maybe in the second column we can see the fiber diameter or some collector diameter, and in the third column we have the quantity of collected water at this collector. We can see that the highest value, 0.27, we obtained at yarn, monofilament approximately 0.2, and these multifilaments or hydrophilic monofilaments are much more worse with the similar fiber diameter or collector diameter. Maybe if we calculate from the values, how much of what is the water layer at the yarn, we can see that the water column on the yarn is maybe 2 times higher than the water layer on monofilament. Now conclusion. We developed a method for the creation of synthetic fog. We made some experiments with this machine. We evaluate some possible collectors. The results, if the material is hydrophobic, we can observe better results than on hydrophilic substrates. And in the case of yarns, we obtain the best results in comparison with other collectors. From this point of view, are the yarns very interesting collectors for the future application for the water harvesting. So thank you your attention, and it's all.